Welcome, ladies and gentlemen, to our lecture on fictitious forces, fundamental forces, and uniform circular motion. So we've been talking about a lot of different forces. We've mentioned weight, tension, friction, the normal force, spring force, pushing or pulling. It seems like there's a lot of forces that we mention, but most of these forces aren't fundamental forces. Most of them have something else going on if we keep looking at a more and more fundamental level. So, for example, we know that as you stand on the ground, that you have gravity pulling down on you, and you have the normal force pushing up on you. But why can't you move through the ground, or a wall, or a table, or whatever else? What's actually stopping you from going all kitty pride and moving right through stuff? So, we'll come back to that in a few minutes and talk about why you can't just move through objects. But let's pull back a little bit and start with two broad categories of forces. Okay, we have real forces and we have fictitious forces. Real forces, the forces that I just listed, that's the kind of thing that we're going to call a real force. These are forces that are actually there. So these real forces, these are things that can show up in your free body diagram. They're forces that we're adding up when we're considering a net force, like when we're dealing with Newton's first or Newton's second laws. A fictitious force is a situation where it seems like there's a force, but there's actually not a force there. And these fictitious forces, they come up because you're in an accelerated reference frame. That's how we run into these things. So this is more clear if we think about a couple examples. And for fictitious forces, cars make really nice examples. So let's consider that, because you're very commonly in an accelerated reference frame when you're in a car. So think of accelerating really hard in your car. You stomp the gas pedal to the floor, and it feels like there's a force pushing you back into your seat. This kind of acceleration force, right, as we're in the car here, and we stomp on the gas, and we feel a force like this. We'll call this our acceleration force. It happens when we accelerate. So let's think about what's actually happening. We stomp on the gas in the car, and the car accelerates forward. Okay? You, on the other hand, are sitting here in the car, and you have inertia. And without something to push on you, you're just going to keep going the same velocity. So if the car was stopped before you stomped on the gas pedal, you're just going to sit there, right? That's Newton's first law. We know that that's true. So what actually happens is we have our seat behind us, and this seat pushes us forward. That arrow is horrible, but it really just pushes us in the same direction as the car's acceleration, okay? So we have a force of a push. And this seat has to push me along and keep changing my velocity when the car is accelerating, okay? So when this happens, you're sitting inside the car and you think of yourself relative to the interior of the car, because relative to that interior, that's where it seems like you're kind of at rest. And you make the car your frame of reference. But the car is accelerated, right? You're in an accelerated frame of reference because the car is accelerating. So you feel this fictitious force. It feels like a force is pushing you back because you're comparing yourself to an accelerated reference frame, the interior of the car. And this feeling all comes back to inertia. And the reality is that your inertia wants you to maintain a constant velocity, but the car is forcing you to accelerate. It's pushing you from behind. But if you compare yourself to the car, to that accelerating reference frame, it feels like there is a force. And that force is pointing in the wrong direction. It's always going to point opposite of the actual force. The actual force is the seat pushing you along, right? Changing your velocity, providing an acceleration. And the force that you feel, the fictitious force, is always going to point in the wrong direction. So the seat pushes me this way, right? And it feels This fictitious force always is going to feel opposite, like it's in the wrong direction. So let's think about when we turn the car. So now let's say this is the car and this is us in the car, and we go around a corner that goes like this. Okay? Now, when you turn in the car, your speed might stay the same, but remember that velocity is a vector with speed and direction. So clearly, when you turn your car, your direction is changing, right? So your velocity is changing. And if we have a changing velocity, then we must have an acceleration, okay? And so once again, when I'm turning in the car, I'm in an accelerated reference frame. The car, as it turns around to the right like this, as it goes around a corner clockwise, is going to have an acceleration that looks like this if it's at constant velocity. So when I turn, as I go around to the right here, it feels like there's a force pulling me out this way, this fictitious force. But again, this force doesn't actually exist, okay? What's actually happening is that my inertia wants me to keep going in a straight line. It wants me to keep a constant velocity. And when I turn, the car has to apply a force to me to give me an acceleration and make me turn as well, right? So what happens is my seat, or maybe my seatbelt, or when you're turning really fast, sometimes you kind of put your arm out on the door here. All of those things work together to provide a force on me that goes back this way, the force of a push. So when you compare yourself to an accelerated reference frame, the car, it seems like there's a force pushing you in the wrong direction, right? Out. Again, this pushes in the exact opposite direction of the actual force here. But in actuality, the car has to apply a force to me in the inward direction in order to make me go around the corner. Otherwise, my inertia would want me to just carry on in this direction. So the takeaway here is this. Be aware of accelerated reference frame and don't add fictitious forces to your free body diagrams. When you feel a force in the real world, be aware of whether it's a real force or whether you're in an accelerated reference frame. So now let's go back to our talk of real forces and let's think about those some more. We have a lot of different forces that show up in our free body diagrams, but if we look more and more closely at them, we realize that something more fundamental is going on. So let's consider tension for a moment, okay? So we have a force of tension, and let's say it's because we have a string on some block. So we're pulling this block along with a string, but if we look closer at your hand, maybe we have a string here, and you have your thumb like this, and maybe your index finger like this, okay? And you're pinching on this string and pulling it. So then, what's actually happening here is right here where your fingers are pinching on the string, we actually have a force of static friction, right? And so when we apply the tension, it's not just some magical tension force, it comes from this static friction force. So we can break it down further and say, well, what we're calling tension is coming from this static friction force. And you may notice this if you ever tried to pull something really heavy with a rope in your hands, and that rope might just slide, right? It slides in your hands because you can't create enough friction force to apply any more tension, right? What do? You squeeze it harder. What does squeezing it harder do? It increases the normal force, right? Our mu s n, that's how we get the force of static friction, right? That's how we get the maximum force. If we want to have a bigger one, we need a bigger normal force. So we squeeze the rope harder, right? Because we can't change this. This is just a property of the skin of our hands and the rope, right? It's a property of those two surfaces touching. So then let's look at the other side of the block. And let's remember that somehow we have to attach this string to the block. So let's say there's a little hoop on the block, okay? Like this, a little metal hoop. And we have the string looped through like this, and then we have a knot in it, and then the string goes out, okay? So when we pull on the string, this string actually presses right here against the hoop, right? That's what actually happens. This little spot on the string presses against the hoop right here. And so then our tension force, our way that we're actually applying the tension force right here, is actually the force of a push, right? It's just like getting behind the block and pushing it. The string pushes on the little ring right here, okay? So when we look more closely, our tension force was due to a friction force on the one side and a push on the ring on this side. And then the rope, it's just actually a fact of when we move one little piece of the rope, if the rope is going to stay one thing, all the other little pieces have to move in accordance, right? So we see that we can consider these interactions more closely, and we can consider how they're actually working. And a lot of times we can break them down into more and more fundamental interactions. So if we keep looking more and more closely at what happens, we eventually get to the fundamental forces of nature. These are the forces that cannot be broken down any further. These rely on the very properties of the universe for their interactions, okay? These forces are the four ways that particles can interact. Remember that forces are interactions, and when we get down to the most fundamental aspects of any interactions between objects, it will always be an interaction by way of one of these four forces. So let's take a look at these four forces. The first one we have here is gravity. And gravity is an attraction between masses, right? We knew that. We've already learned that. This is a fundamental force of nature. So when we consider your weight, that can't be broken down into interactions based on other forces, like we did with the string example, okay? Your weight is a gravitational interaction between you and the Earth. All masses are attracted to each other through gravity. So gravity is, in fact, the curvature of space-time. And that's one of the discoveries that Einstein is best known for. But we're not going to get into that aspect of gravity further in this class. It's just a nice thing to know in general. So for our purposes, we'll consider gravity to be just a simple attraction between masses that acts at a distance. Okay, so I have mass 1, and I have mass 2, and they are attracted to each other. Okay, we'll draw attraction with the arrows in the middle like that. And gravity is what holds things like planets, stars, and moons together. Gravity is the reason that all those things are round. It's what makes objects fall toward the surface of a body, and it's what causes bodies to orbit each other. Gravity is the reason that the moon orbits the Earth, the reason that the Earth orbits the sun, and the reason that the sun orbits the supermassive black hole at the center of the Milky Way. Okay? Gravity is a really powerful force as we talk about really large objects, okay? But when we talk about really small objects, gravity isn't really very important. And that brings us to our next force here, the electromagnetic force. The electromagnetic force is involved in almost everything that we see on a daily basis. There's so much to learn about the electromagnetic force that it's the main focus for most of your next class in physics, Phys 272, I think. The electric force arises from an attraction or repulsion based on electric charge. And electric charge is a property of particles. We can have positive or negative electric charge. And this property of particles goes right down to the fundamental particles of the universe, okay? Even the particles that are not made up of other particles have electric charge. Most of them. So we have these positive and these negative charges. And opposite charges like this are attracted to each other. And like charges, plus plus like this, they're repelled away from each other, okay? Or minus minus. So when I have charges like this guy wants to go this way and this guy wants to go this way. And if we think about chemistry, and we think about the atom, we'd say the atom is made up of 3 particles, okay? It's made up of the proton, which has a positive charge, the neutron, which is electrically neutral, it has no charge, and the electron, which has a negative charge. So the nucleus of an atom is made up of protons and neutrons. So it has protons in it, and it has neutrons in it. And the number of protons is the chemical element. Okay, so hydrogen is an atom with just 1 proton in the nucleus. Carbon is an atom with 6 protons. Oxygen with 8 protons, and so on, okay? The whole periodic table, every element in the universe, the only difference is how many protons are in the nucleus, okay? And that gives them all of these different properties that they have. We know that different elements have different properties, right? We know that oxygen has different properties than, say, lead. But the only thing that makes them different is the number of protons in the nucleus. Then we have electrons that form a little shell around the nucleus, okay? They form multiple shells, in fact, around the nucleus. And these shells are negatively charged because they're made out of electrons, okay? The electrons are bound to the nucleus by the electric force, by this electromagnetic force. They have a negative charge, and the nucleus has a positive charge, so they're attracted to each other. The atoms can then bind into molecules, okay? So one of the most famous ones, we have an oxygen bound to 2 hydrogens, like this, to make water, right? And those molecules build up the macroscopic objects that we encounter in everyday life, okay? So then we would have maybe multiple water molecules binding to each other to make, say, ice. I don't know what structure they have, but something like this, say, okay? And the atom is held together by the electric force. This molecule binding happens from sharing electrons in their electron shells, so it's powered by the electromagnetic force. And then molecules binding together is often caused by London dispersion forces, among a couple other ones, but also all powered by the electromagnetic force, okay? So all the objects that we deal with every day, they're built up from atoms, which make molecules, which build up macroscopic objects. And it all relies on the electromagnetic force. And this brings us back to the question I posed at the beginning of the lecture. Why don't you pass through other objects? When you place your hand on a desk, why can't you pass through the desk? When you walk into a wall, why do you bump into it and hurt yourself instead of passing right through it like Kitty Pryde? So remember that molecules are made up of atoms, and the atoms have these electron shells around them, okay? At the macroscopic level, the atom and the molecule are neutral. So I have a positive thing surrounded by an equal amount of negative charge here. So when I put something else out here, object 1, from this distance, this just looks like a neutral thing, right? Inside this circle, I have the same amount of positive and negative charge. So on the macroscopic level, if this is, say, my hand, and this is the desk, they're not attracted to each other by the electric force because they're both neutrally charged. We can't feel the electric force pulling our hand into the desk. But if we keep forcing them closer and closer together, if we keep moving our hand closer and closer to the desk, you can see that as I move this object, if I put object 1 right here, okay, and it has its own nucleus and electron shell, then it starts to matter, right? Then if I have another nucleus like this and another electron shell that's minus and plus, now my minuses, it's going to start to matter, okay? They're a lot closer. They're interacting now independent of the whole thing, right? And the pluses are further apart. And this is what actually stops you from going through things. Ultimately, the electron shells on these atoms repel each other, and the electromagnetic bonds of molecules hold your hand and the desk together so they can't just come apart and mix. And so the fact that the molecules won't rearrange and they have these electron shells that push on each other, well, that stops your hand from going past the desk, okay? So a whole bunch of our forces of push, our force of tension, our normal force, all of that stuff is ultimately a result of this electromagnetic force, because it's all a result of the fact that we can't take solid objects and just push them right through each other, okay? So the electric force is responsible for the vast majority of the macroscopic objects that you interact with, and it's responsible for the fact that solid objects can't pass through each other. The only force that we'll really deal with regularly in this class that doesn't ultimately boil down to an electromagnetic interaction is gravity. Okay? We'll deal with gravity regularly, and gravity does not ultimately come down to an electromagnetic interaction. It is a fundamental force of its own. So we can use these two forces, electromagnetism and gravity, to explain the macroscopic interactions that make up your life. But then there's these two other forces, okay? So let's look at the strong force first. The strong force is a force that acts to bond certain kinds of particles together, okay? So remember that I told you an atom, its nucleus was made up of protons and neutrons. And then they have the electron shell out here. Electrons are an elementary particle. They're not made up of any smaller particles, okay? They are among the basic kind of Legos of the universe. So electrons are elementary. Protons and neutrons are different, okay? They're a different kind of particle called a hadron, and hadrons are made up of quarks. So a proton is actually made up of smaller particles called quarks. So we have these three little quarks, and they make up a proton. And a neutron is also made up of quarks, all right? And quarks are fundamental particles, like an electron. They're not made up of any smaller particles. They just are particles, okay? The quarks are held together by a force called the strong force. This force right here. And this force is extremely strong, but it can only act over short distances, okay? So the strong force relies on a more complicated kind of charge that we call color charge. But we call it color charge because colors don't really mean anything, okay? And it's just a more complicated charge that has three different charges, okay? And we call them red, green, blue. But the fact that we call them color names, it doesn't mean anything. It's just there's three primary colors, so somebody started calling it color charge, and that's what it's called, okay? We're not going to go into this charge anymore in this class. This is far, far beyond our class, okay? So don't worry about color charge. Just know that the strong force relies on a kind of charge that has three charges instead of just two, like the electric force. So let's go back to the atom. And I told you that the atom was made up of protons and neutrons, but that should have raised some red flags, okay? And the reason it should have raised some red flags is because I told you that like charges repel each other, right? So we have a plus, and that's going to make them want to go like this. But this nucleus up here, it's got a bunch of plus charges just sitting around next to each other. So if they should be repelling each other through the electromagnetic force, and we know that the electromagnetic forces can be pretty strong, why are they just sitting next to each other? And the answer is the strong force, okay? At the scale of the atomic nucleus, the strong force is much, much stronger than the electromagnetic force, okay? So even though the protons would electrically repel each other, the strong force holds them together, okay? It holds the protons and the neutrons all in this one nucleus here so that we can have an atom, okay? Now, the strong force has a very limited range, so it doesn't interact at distances outside of, say, the atomic nucleus, okay? And we don't really see it in everyday life, but it's essential to nearly everything in the universe since it's the reason that we can have atoms. And we already talked about the fact that atoms make up everything else in the universe, right? So the fact that the strong force enables this atomic nucleus here makes it absolutely essential to the universe as we know it. But in our daily life, we don't ever interact with the strong force. We don't see the strong force doing anything because it has such a short range that it can't really act on ranges outside the size of an atomic nucleus. Okay? So strong force is really strong, but really short range. Our last force here is called the weak force. And this is the last of our fundamental forces. And if we called the strong force because it's strong, you can guess what's interesting about the weak force. The weak force is also short range like the strong force. So it also just kind of works inside of atomic nuclei like the strong force did. And again, the weak force is weak, okay? We call it the weak force because it's not strong. We generally see the weak force in a certain kind of radioactive decay, okay? And again, that's far beyond what we're going to discuss in this class, but it's there and it causes this radioactive decay, okay? And it also allows certain kinds of particles called neutrinos little neutrino here that do not have an electric charge or a color charge to interact with other kinds of matter, okay? So my neutrino here has no charge for both the electromagnetic force and the strong force, okay? It doesn't have a positive or negative charge, and it doesn't have a color charge. So it can't interact by way of either of those forces. It can interact by the weak force, okay? And in that certain kind of radiation, a neutrino is usually emitted, okay? And because the weak force is both weak and short range, neutrinos only very rarely interact with matter, okay? So streams of neutrinos are passing right through the Earth, through all of us, at all times. But they only interact with any of the matter of the Earth on very rare occasions, okay? It turns out that these neutrinos are emitted when we have fusion in the sun, and so the sun streams neutrinos at us. But since they only interact with matter so rarely, they basically just fly right through us, right through the Earth, and just never interact with anything, okay? Only on the rarest occasions do they interact with anything. And we build enormous detectors in the ice of Antarctica to see these really rare reactions. So we talked about each of the four fundamental forces, and we know that we only see gravity and the electromagnetic force in our macroscopic daily lives because these two are short range, right? They really just kind of occur in the atomic nucleus. But let's talk for a second about the relative strengths of these forces. So these two forces are long-range forces. And we would technically say that they have infinite range, but in a practical sense, we know that if we're far enough away from something, we can ignore the effects of gravity or of the electric force, okay? These two forces, like we said, are short-range forces. We only really see them acting at scales of the atomic nucleus or smaller. But the strength of these forces is also vastly different. And that's what we have in this column here, okay? So we've compared everything here to the strength of the strong force. And it's called the strong force because it's strong, okay? This one is the Hulk or Thor. This guy is much stronger than all of the other forces. And that's why it can overpower electromagnetism to hold atomic nuclei together. We see the weak force is about 1,000,000 times weaker than the strong force, okay? And that's why interactions with the weak force generally rely on particles that are already in bound states because of the strong force, or particles that don't have a charge in the electric or the strong forces, okay? And then finally, we have gravity and electromagnetism, okay? The two that occur at the macroscopic scale, right? We see that the electromagnetic force is 1/137th as strong as the strong force. Now, compared to the weak force, and we'll get to gravity here, that's pretty strong, actually. Only 1/137th is a lot better than 1/1,000,000th as strong, right? It's a whole lot better. So the electric force is pretty strong. And then finally we have gravity that we see up here. And gravity is 10 to the minus 39 times as strong as the strong force. That is really, really weak, right? That's way weaker than the weak force, which we call the weak force because it's weak. So what's going on there? It's basically so small, it's not even there. compared to these other ones. And indeed, when we're dealing with things at the atomic level, we don't even care about gravity. We can predict quantum mechanical outcomes with unbelievable precision without any consideration of gravity whatsoever. Okay? We do it all the time. But as we walk around on Earth, gravity seems pretty important, right? When I slip and fall on some ice, gravity doesn't seem so weak to me. And I told you that gravity is holding planets and stars and galaxies together. So what gives? If gravity is so weak, how does gravity come to rule the universe on the large scales? How does gravity lead to stars and galaxies and clusters of galaxies and black holes and all this other stuff? How can gravity pull a planet together? So we know that when we're dealing with large scales, we don't have to worry about the strong and weak forces anymore because of their range. So we're done talking about those really for the rest of the class, right? We're done for today, and that means we're done for the rest of the class. The strong and the weak force are gone. So for macroscopic objects, that leaves us to consider the electromagnetic force and gravity. So let's look at the electrostatic force. We know we need charges for the mass to interact, right? So let's say we have a plus and we have a minus. We have to have these opposite charges for them to be attracted, right? But if I put these charges close to each other, if I move the minus right up next to the plus here, then if I think about that as now one object, they're bound, they're stuck together, the plus and the minus. When I have my other object over here, we even already talked about this. This looks neutral to this other object, right? Now that they're far away, this object is about as far away from the plus as it is from the minus. And so together, the effect is that it just doesn't see any electric charge, right? So now my new object here, this guy that's made up of the plus and the minus, it can't really attract any other objects through electrical charge, right? This guy isn't going to be, even if he has a charge, let's say he's plus, he's not going to be attracted to this guy because this thing looks neutral. Okay? So it isn't attracted or repelled. And that's why you don't feel an electric pull toward the objects around you. Okay? Your atoms and molecules are almost all neutral. They have the same amount of positive and negative charge, right? So they're neutral, and that makes them not attracted through the electromagnetic force to the other objects around them, which also have neutral atoms and molecules that make them up. So it's hard to build up a really big object this way. We know we can build up pretty big objects, right? We could build up, say, a truck or a person or a big rock or something like that. But it's hard to build up a really big object like this because things aren't attracted to it. But now let's look at gravity. And let's say we have these same two pieces, okay? But now instead of the charge, because gravity doesn't care about electric charge, they have mass, right? M1 and M2. And we can think about mass as kind of gravity's charge, okay? So we said the strong force has 3 different charges. The electromagnetic force has 2 different charges. Well, gravity has charge, but only has 1 charge. Just mass, okay? And mass is always positive, okay? So then I have this pair of objects. Let's say that they were plus and minus, so they're electrically neutral. And I've added these 2 masses. And they're all gravity cares about is mass. So the mass that the first object had plus the mass of the second object is now the mass of this object. And we know that gravity is stronger when there's more mass, okay? Mass is like gravity's charge. So the more mass I accumulate, the stronger gravity gets. And you can see there is no canceling effect. When I'm not adding a bunch of positives and then a bunch of negatives and they kind of cancel each other out like the electromagnetic force. When I add stuff, I just keep getting more and more gravity. So as I add masses, and I add a mass, and I add a mass, and I keep adding masses, this thing's gravity just keeps growing, okay? My new object just has more and more and more gravity. In fact, As I start to gather a lot of stuff, like when a planet is forming or a star is forming, then I have so much gravity that other little masses that are hanging out over here, well, they'll start to just show up on their own. The gravity itself will suck them in. And I'll keep getting bigger and bigger. And these huge objects like planets and stars and galaxies are all electrically neutral as they add atoms. But all that mass adds up and we just get more and more and more gravity. So even if the force is weak in terms of how much you can get per atom or per proton, it only adds up. It doesn't ever subtract. And so if I add more and more and more, even if I add little tiny numbers, really tiny numbers, if I add enough of those tiny numbers, I can start to get a big number, right? I can start to get a big magnitude. And that's how we end up with these objects that have such strong gravitational pulls, like the sun, or for us, the earth, right? In fact, our weak little force of gravity can become so strong when we get enough mass in one place that it overpowers all of the other forces, okay? And it all comes back to that infinite range and the fact that its charges don't cancel. So that's our bird's eye view of the fundamental forces. All interactions can ultimately boil down to an interaction via one of these four forces. And for our purposes in this class, all of our interactions are either going to be gravity or can ultimately be explained by the electromagnetic force if you dig into them far enough. Okay, sometimes you have to dig in pretty far, but if you go far enough, you'll always boil it down to the electromagnetic force, or it was gravity. Okay, it was an object's weight. So now let's switch gears entirely and let's talk about uniform circular motion. Okay, let's talk about something that'll let us model some more physical systems at the level of this class, and I want to cover this uniform circular motion here just briefly, okay? So uniform circular motion deals with an object traveling in a circle. So if we have a particle right here, the particle is going to go around the circle like this. Uniform circular motion, our object travels with a constant speed, okay? The velocity, of course, is always changing because its direction is always changing, but the speed is constant. And remember that a circle is an object with a fixed radius from the center. So for a curve to be a piece of a circle, it would have to have a constant radius of curvature, okay? And our uniform circular motion can deal with either objects going in complete circles or objects going through curves with constant radius of curvature, so pieces of a circle. So maybe I'm in a car and I go through a corner that would be this much of a circle, okay? That I could also use uniform circular motion to model. So when we move through a curve with constant velocity, we have an acceleration that points toward the center of the curve, perpendicular to our velocity at any given moment in time. Okay? So as we travel around this circle, this acceleration here always points toward the center of the circle. So when my particle's here, the acceleration points like this toward the center of the circle. And our velocity is actually always tangential to the circle, okay? It always goes kind of straight like this. So as we go to different points, we have velocity like this and acceleration like this, always, okay? V and A, as we go around the circle. So we usually call this acceleration centripetal acceleration, or center-seeking acceleration. And this acceleration has a magnitude, A centripetal, equals V squared over R, where R is the radius of the circle, and V is this V here, the velocity that the particle has. Sorry, let me be more specific. The speed that the particle has, okay? The magnitude of the velocity. The direction isn't in this, right? So this is only giving us a magnitude of centripetal acceleration, right? The direction we have to know always points toward the center. But this equation here, this formula, gives us the magnitude of centripetal acceleration. And because this acceleration is perpendicular to velocity, right? We see here it's perpendicular. No part of it points in the direction of velocity, right? If it was like this, then if we broke it down into components, we would see that a little bit of it points in the direction of velocity, right? But it isn't like that. It's like our coordinate systems, where it's completely independent of velocity. And so it doesn't change the speed of the particle at all. It only changes the direction of the velocity. So when we have this uniform circular motion, if we travel a full circle, one full time around here, we call that one full circle one period, okay? And we usually notate period with a T. And a period is the distance covered, okay? And for a circle, that means 2 pi r, right? And then, just like we considered the relationship between displacement, average velocity, and time, this one's going to be divided by this speed, okay? And we see that what we get, if we do units, is meters over meters per second, right? And the period then is going to be a time. And the period here is the time it takes for one complete revolution. So if we have centripetal acceleration, and we know that accelerations are caused by forces, remember F equals ma, then we must also have a centripetal force, okay? But let's be clear here. MAC is not a force, okay? It's what happens when there is a centripetal force. There is no independent centripetal force, okay? Something has to provide a force that acts as the centripetal force in your system. So for example, if this drawing is Earth's orbit around the sun, then there isn't some independent centripetal force. We wouldn't add a centripetal force on a free body diagram of the Earth. Gravity pulls the Earth directly toward the sun, which is at the center of the Earth's circular orbit. So gravity, Fg, provides the centripetal force, okay? And this causes Earth's uniform circular motion, to an approximation, okay? Earth has actually a pretty close to circular orbit. So if we had, say, a ball on a string instead, going in this circular path like this, okay? Then the string here, tension, would provide the centripetal force, okay? The ball wants to fly straight, but the string keeps pulling it toward the center of the circle and forcing it to turn. Now, if at any time that centripetal force stops, okay, so let's say if the string breaks, the object then won't have any net force on it, right? And so it will keep going with a constant velocity. Constant velocity means constant speed in a straight line. So at all points, the velocity is pointed this way. So if the string breaks, the ball will fly this way, okay? So if the string breaks while the ball's over here, of course, we would get this way, right? Oh, let's try to make that a little straighter. Okay, we didn't really succeed. And if it breaks here, it goes this way, okay? Always tangential to the circle. Now, we often think that an object will go outward if the string breaks, if the string breaks, but this is not actually true, okay? When we're thinking about that, we're thinking about the ball in an accelerated reference frame, and we get caught thinking about a fictitious force. We think there's a force pushing the ball outward as it travels in a circle, but there isn't, okay? It's in an accelerated reference frame. The actual force is the string pulling the ball inward, and the velocity is always tangential to the circle. So at any point, if we stop applying that force inward, then the object will have a velocity that doesn't change, and it will continue on whatever velocity it has at the moment that we stop applying that force, okay? And that is this tangential direction. So if you think about taking a child by the hands and spinning around, right? Their kind of legs go up in the air, and you can just spin with them like that. And they usually find that pretty fun, right? I want to be really clear here. There is no force pulling out on them, okay? When I hold their hands and I spin around, what I'm doing is very similar to when I turn a corner in a car, okay? There is no force pulling outward. I'm giving them a velocity, and their inertia makes them want to travel with a constant speed in a straight line. Me holding onto their hands is applying a force inward and forcing their velocity to change direction, okay? The feeling of being pulled outward, the little child would probably feel like they were pulling outward. It comes from being in an accelerated reference frame, okay? They're in a reference frame that's spinning, and that makes it feel like there's a force outward, but it's a fictitious force, okay? So centrifugal force is a fictitious force. There is no centrifugal force, okay? There is only centripetal force, which pulls inward. So when we solve problems with uniform circular motion, we will definitely never be drawing a centrifugal force, okay? This does not exist, okay? So we'll get to work more with uniform circular motion by solving some homework problems and some example problems in the future. So we'll have more exposure to that topic as time goes on, and you'll get a lot more familiar and a lot more comfortable with that topic.